ஆதி அந்த அவருடைய லிங்க் மட்டும் எடுத்து அனுப்பு. அவருக்கு வர தெரியல உள்ள போயிட்டு. பசீரோவுக்கு நம்ம அந்த மெயின் லிங்க் எடு, வாட்ஸ்அப்ல எடு. கீனோட் செஷன் லிங்க் மட்டும் எடு. அந்த இது அவருக்கு தெரியல. வாட்ஸ்அப் பண்ணுங்க. அப்படியே அந்த மாதிரி வச்சிருக்கல, அதை அப்படியே எடுத்து எனக்கு வாட்ஸ்அப் பண்ணுங்க. இப்படி இருக்காங்க ஒரு எந்த நியூஸ்ல படிச்சாலும் காமன் சென்ஸ் இவ்வளவுதான். நான் தான் சொன்னேன் மேடம் நேத்தே, இதெல்லாம் ஒர்க் அவுட் ஆகாதுடா, புரியாது அப்படின்னு. எல்லாம்
sir, hello sir, welcome sir. Dr. Brenda from Sairam Engineering College. Sir, kindly unmute yourself, sir. Hello. Sir, welcome, sir. Sir, shall we start the session, sir?
Hi, can you hear me?
Sir? Sir, if you want to share something, you can share the screen, sir. Then we can confirm. Hello, sir.
Hi.
Yes, sir. Yes, sir. Now you are audible.
Okay.
Yes,
Now
sir.
you can hear me?
Yes, sir.
Okay, thank you very much.
Welcome,
And,
sir. Welcome to our conference.
Okay. It was not possible to connect before because I didn't receive any invitation for a right session. So now it's 10 o'clock in the morning in Italy, and I still have half an hour after I have lesson. So if you want, I can start immediately
Yes,
my presentation, and I will stop in half an hour. Okay?
Yes, sir. Yes, sir. Definitely, sir. Yes, sir.
Okay.
What you get by achieving your goals is not important as what you become by achieving your goals. Now I would like to welcome Professor.
Okay, I share my screen.
Yes, sir. Yes, sir.
Okay. Can you see my medicine 4.0? Yes?
Yes, sir. Visible, sir.
Okay, I will begin now. Okay, thank you very much. Good afternoon to everybody and good morning for me. I hope that everything is okay with the audio and video. And today's presentation is the second presentation I'm showing you after the first one dedicated to medicine and artificial intelligence. This time I will try to give you more news about this. And so the outline is always dedicated to telemedicine and electronic health and new wearable devices and the concept of artificial intelligence, machine learning, and deep learning for telemedicine, and which items are relevant to the instrumentation and measurement society to consider an artificial intelligence approach. Okay, everybody knows that in these last years, we spoke a lot about electronic health and telemedicine. You can find a lot of definitions in internet, but I think that the best one is to say that electronic health is related to technologies, where technologies means to have a new technology to help patients in their illness. So e-health is electronic devices, electronic tools, and so on. Telemedicine is how we use these technologies to remotely diagnose, monitor, and treat patients. So in this way, we should be able to help people in today's life. So why telemedicine? Everybody knows that today the number of people all over the world, in Italy and in India, of course, is increasing. And also people life expectancy is increased. not in these last years due to COVID, unfortunately. By the way, if we consider 100 years ago and today, we see that more than 20 years of life is a life expectancy. So we have to think to a new approach, of course. And COVID-19 was a strong indication about limitations of traditional medicine. And the problem today is how can a doctor visit a patient when the patient is affected by dangerous situations. So thanks to electronic health, we can have devices which can be used in a remote way without any medical doctor present in the same room. So this is the idea. And for example, in this presentation, I will consider three parameters that are quite important in monitoring the patient situation. And electrocardiogram, this is today always the main tool to find the problems in your heart. Remember that also with COVID, really atrial fibrillation and cardiological disease are still the main cause of death in the world. So this is the first important item. Photoplethysmography, again, can give you important information about the efficiency of your respiratory system, the percentage of oxygen in your blood. And today, with COVID, this is a quite important parameter. And image processing. Image processing is again an item very important, which can be related to several pathologies. So image processing is again a problem which can be solved using electronic health systems. So last item, but I think the first item is that you can find a lot of devices today, but unfortunately, they are quite difficult to be used. So elder people will be the main users of these tools. So the idea is to develop simple devices to be used by elder people without fear. Okay, so this is a lot of possible applications, but I think that we can have a look. Unfortunately, this is in Italian, but I will try to translate for you in real time. Okay, you see, this was our first ECE watch. It's just a watch and an app, a very low cost app for smartphone. And you see that the user can launch the app on the smartphone, and with a simple system, also elder people can. You can use your finger for just 10 seconds and see the electrocardiogram. If you have a doctor, he can immediately see the electrocardiogram without any complex system to be connected. If you are an elder people, you are not interested in study your electrocardiogram, but you can send it by email. So we suppose that but smartphones today are connected to internet everywhere, and the remote doctor can have a look at your electrocardiogram to measure time, to check atrial fibrillation, shock QT, brugada, and other important things. So this is the idea, to have a very simple and low-cost system, just like a watch, tied on your wrist, and a remote doctor is able to check your health. Today, this is, completely different, because you need to go to a medical studio and to address, and the medical doctor will use his systems to make this electrocardiogram. So it's a very long procedure. Our idea is that 10 seconds is important to save a life. Okay, and second, but not the last, if you have e-health systems, You can short the hospital stay after surgery, for example. You give these tools to a patient which can be go to his house and you will check his equation, his vital parameters in remote. You don't need paper, you use electronic paper. You don't need to travel. You don't have to lose the time. And so, okay, this is not total. I mean that for serious disease, we still need a complete electrocardiogram and a medical doctor in presence. Okay, but often it's important to detect atrial fibrillation because this is the first item to be considered. And atrial fibrillation can be detected with our small ECG watch. And so you have to go to the doctor's office only when you need, but you can check your problems also by yourself. Okay, very fast because we don't have the time. This is a slide collecting the industry 4.0 because everybody is speaking of industry 4.0. Every 100 years, a new step can be considered from industry 1.0 to industry 4.0. Today, artificial intelligence, internet of things, and our things are connected to this. Medicine is slower, so it's difficult to identify every 100 years a new item, but this is a sort of classification. Medicine 1.0 was when Crick described the DNA structure. This is very important. A second step is when we were able to sequence the human genome and to find the origins of disease. 3.0, okay, when we engineer and biology decided to work together, and this is quite important because two different knowledge were put together. And today we can speak of medicine 4.0 with the process digitization, when communication and our functions are available in the health system. We have to measure parameters. We have to consider accuracy. Here, the instrumentation of measurement exercise can give us significant contribution. So, what goals do we have to check everybody all over the country? And we can monitor remote blindness and prevent the dangerous conditions. Remember that when you detect atrial fibrillation, maybe you can have a few minutes to check your situation with a doctor. So the idea is new technologies for smart sensors. Telemedicine, okay, telemedicine is a word. Often I see that telemedicine is intended as a front phone, where the patient is able to speak with medicians using a smartphone. Okay, this is important because often the patient is alone, has requirements to speak with a medical doctor. So this is important, but the medical doctor has no knowledge about the vital parameters of the patient. This was the first answer here in Italy to give a doctor a small, not small, a small set of instruments, and the medical doctor was able to go to the house of the patient and to measure all these parameters: ECG, SpO2, blood pressures, temperature, and so on. Okay, with COVID, the problem was that the physician has to protect himself against the virus. So no more than 10 patients a day, very expensive approach. So the idea is that we need the new clinics for okay, and this is a possible choice for electrocardiogram. You have available both laboratory instruments ALA, or you can have also commercial power. You can check here, for example, heart rate, to see the electrocardiogram, to measure the SpO2, and to have values of arterial blood pressure. Everything is remote. I mean that a patient has this instrument and is able to send the data to a medical doctor in a remote way. And this is quite important because it's an extension of the telemedicine concept. Not only the patient can speak to the doctor, but the doctor can see the situation of the patient. Okay, the second item of this presentation was related to artificial intelligence. How is artificial intelligence related to telemedicine? Okay, we have to find dangerous situations. For example, in cardiological disease, you have a lot of dangerous situations. And artificial intelligence today is used to reproduce the doctor interpretation. Okay, so the idea is not to replace doctors, but for meaningful evidence to have a tool which is able to emulate the doctors to check dangerous situations. And what's the difference between artificial intelligence and doctors? Because you can say, but we know how to detect upper fibrillation. There is an algorithm checking the air pitch and the T wave and so on. Yes, yes, this is true. And the difference is this: when you have an algorithm, you can send the data to a classical program and to have answers. Okay, so this is enough for several cases. Problem is when we are not able to find an algorithm, or when it's too computational expensive. Sometimes we have an algorithm, but you need hours for computers to have an answer. And in our situation, the algorithm is not suitable for some people. So this is the limitation of classical programming. Answer can be using artificial intelligence. Here I distinguish among the different approaches. Artificial neural networks, for example, or machine learning, you can give both data and answers to a machine learning program. This program is not related to the specific problem. I mean that you have a general tool called machine learning or artificial neural networks. You give data and you have answers in form of patterns. Okay? This is a new way. I mean that you don't need a specific algorithm to detect other things. The same machine learning technique can be used for upper fibrillation, for example, or for short QT related to Q and T waves and others. Okay, so just like a medical doctor, when a medical doctor is able to see a lot of patients, he will be able to understand some programs. Of course, we need a lot of data. So the evolution of artificial intelligence, artificial neural networks, one is a spatial model which is more suitable to human brain. They are called the deep neural networks and can be considered in an instant. You see here, for example, in input, you have ECE signals, and in typical approach, you have the brain of a medical doctor able to give a diagnostic conclusion. But the same ECG can be given to a deep neural network, which is able to give the same diagnostic conclusion. So if we need to make a lot of analysis and you don't have a medical doctor dedicated to every case, okay, so you need a lot of time, of course, so you can use this automatic tool, this automatic artificial intelligence tool, able to make the same diagnostic conclusion. Okay, this is the idea, and for some application, we can find a solution. Here I have few time, only 10 minutes, unfortunately, and I present here an important approach that we found to measure the blood pressure. The blood pressure in hospital can be checked using an invasive system, using usually in ICU, and you use a catheter into an artery and display the measured pressure on a monitor. Okay, this is used in ICU because it's strong invasive. You can't think to use it in your house. Okay, so usually when you need to measure your blood pressure, you use a sphygmomanometer. A sphygmomanometer is an inflatable cuff around your arm. You can have a healthcare professional able to measure your pressure in this way, or you can use a self-measuring blood pressure monitor. Okay, for example, in your wrist and our. Okay, these two systems are not so precise as invasive, but okay. In both cases, main problem of sphygmomanometer and wrist manometer is the position. So when you work by yourself, the precision of position of these systems is related to the precision of the blood pressure measurement. So really, we can have some problems, maybe 10% of wrong measurements due to wrong position of the systems. So this is a problem. Unfortunately, the first solution is not suitable for most of them. You can see, okay, coming back to the programming approach, do we have a mathematical model of a blood pressure? Yes, we have some models. For example, to measure the pulse wave velocity for an arteria. And this is a very good measure, but you need to measure the vessel diameter, the blood density, the thickness of the vessel. Okay, this is a very academic model, but it's very difficult to measure it really. So we could have a mathematical program, but we are not able to use it. Other models, yes, we find other models in the medicine literature where you measure the pulse transit time. Okay, again, you have a lot of parameters related to your blood, to your vessel. So usually you are not able to measure this parameter, or you are not so precise. So again, this model gives you poor precision. Okay, so let me again come back to the methods that we can use. Invasive catheter inside your arteria, very precise, okay? But you can have a pain, you have infections, so no good. Sphygmomanometers, you can have a caregiver or you can use by yourself. It's not invasive, it's less accurate, okay? And this is today's situation. But let me check our parameters. If you come back to measurement of electrocardiogram, photoplethysmography, and invasive blood pressure signal, we can find relationship between all these measures. So here I give you an electrocardiogram, a photoplethysmography, and using these two parameters, I'm able to give you the blood pressure signal. This system was used applied to MINIC database, that is a big database from USA with electrocardiogram, photoplethysmography, and blood pressure values. So we were able to use a new system to check the pressure using artificial intelligence systems. Okay, we used deep neural networks and other networks to check the situation. Okay, now we don't have enough time. Here are the steps that we have to use to join a good result. But I can give you results using these networks. So the idea is to have blood pressure starting from PPG and ECE. We are able to check ECE and PPG with very simple, low-cost and precise system. And using artificial neural networks, we are able to predict a very good blood pressure. Show you. Okay, we use the spatial neural network called the convolutional neural networks. My idea was to present all these steps next time, maybe. Okay, and we use the several models to improve our performance. And at the end, I can show you these results that are very interesting. And using sphygmomanometers and artificial neural networks, we are able to have values for systolic and diastolic blood pressure compared to the sphygmomanometer systems. And in this slide, I can show you that we use the training set coming from a MIMIC database and coming from my lab, where 9 healthy volunteers were recruited to participate in this research, and using our instruments to measure only ECC and PPG, so very simple, no cuff, no positionings, and so on. Here you see different neural networks jump at this, and this is the final result. And we are able to have a blood pressure value better than the sphygmomanometer. So the idea is, if we have enough data to train a deep neural network, we are able to measure blood pressure without any cuff, any catheter, any algorithm. This is very important because only data were used to find these results. Very interesting approach. And this is our instrument. You see that, again, we use only a finger to measure both ECG and photoplethysmography. And we have a final result better than sphygmomanometer. Using this system with real humans, we found that we need to personalize our measurement, because we found that every person can have a different relationship between ECG and PPG. And so we have to apply a personal training for every person to have the right values of blood pressure. Okay, this was supposed to have another case, but we don't have enough time. And so I think that I only have 2 minutes to conclude my short speech. How can we do a remote analysis of medical data? Okay, first of all, we need devices able to take data from a remote patient. They must be simple, they must be low cost, cheap, okay? And this is the first step. This data can be used in a local way, using a smartphone, or sent by email to a remote diagnosis system. And I showed you that using artificial intelligence, that is deep neural networks in this case, we are able to have very good results for blood pressure just using a deep neural network. So we don't need a medical caregiver to use a cuff and so on. So a remote system is able to give you value. Why instrumentation and measurement societies can be important? way, because the precision accuracy of these electronic systems must be validated. So we have analog values that are converted to digital and transmitted using smartphone. And so we use an analog neural network to perform a digital analysis. Is everything okay? It's an open question. More, artificial neural networks are considered black boxes. This is true because when you use a deep neural networks, for example, you have a lot of strange neurons and synapses evaluating your data, but we don't know nothing about the meaning of internal neurons in a deep neural network. So the question is how reliable can be considered. Most medical doctors are not happy to use these black boxes without the control of the system. Okay, I think that we have good results, but maybe if we have to validate all this system, we must. Last but not the least, everybody using neural networks know that the best aspect of neural networks is the capability to generalize. For example, if you use the neural networks to read the characters, a strong point of neural network is the capability to distinguish A from B or to recognize A, character A, I mean, written in different ways. This is a strong point of generalization. But in this case, we use deep neural networks to measure a precise value. So, is this a strong point or a weak point? This will be the future research in this field. So to finish, all over the world, we have a big discussion about the use of telemedicine, joint with artificial intelligence to measure medical data in different ways. Maybe this approach can overcome weak points of the traditional data. Okay, these are the good points. And today we still have to validate the results and to consider accuracy and the precision. Okay, I was able to stay in my limits. Fortunately, we started very late, but this is okay. I will be happy to send you answers if you send me an email with papers and other details. Thank you very much to everybody.
Share downloads. Any questions?
Thank you, sir, for sharing your knowledge with us. Students, do you have any questions?
Share screen. No question.
Thank you, sir. Sir, I request you to accept this e-memento as a token of gratitude. Please, sir.
Okay, thank you very much. Thank you very much to everybody. I'm really sorry for the short presentation due to technical problems, and I hope to be able to give you more information when you need. Thank you very much.
Thank you, sir. Thank you for your valuable presence and presentation. We will meet with the other presentations, sir, in the future. Thank you, sir.
Okay, bye. Bye.
Bye.
All you need is the plan, the roadmap, and the courage to press on to your destination. Here we have Professor Dr. Nuno Bogas, Director, DEPI, President,
Hello, sir. Dr. Nono, sir. Shall we start?
Yes, can you hear me?
Yeah, sir.
Okay, thank you.
Sir, if you want to share something, you can check it, sir, before the presentation.
Okay. Oh, sorry. Yep. Okay.
Yes, sir. Screen is visible. Okay, sir. 1 minute, sir.
Okay, no problem.
Here we have Professor Dr. Nuno Bogus, Director, DEPI, President, IEEE MTT, and Chair, URSI Commission. He received the diploma and doctoral degrees in Electronics and Telecommunications Engineering from the University of Aveiro. He is currently a full professor and a senior research scientist with the Institute of Telecommunication and an IEEE fellow. He is the editor-in-chief of the Cambridge Wireless Power Transfer Journal and an associate editor of the IEEE Microwave Magazine. Sir, now I welcome you for sharing your thoughts on the topic simultaneous wireless information and a power transmission for space exploration. Please, sir.
Okay, thank you. Thank you very much for your invitation, and it is really a pleasure to be here today to talk to you about simultaneously wireless information and power transmission. I call it from IoT to space exploration because I think these techniques have implementation in several areas. So let me first briefly start to tell you where I came from. I come from Portugal. Actually, Portugal is a small country in Europe, very close to close to the Atlantic Ocean, and I'm coming also from a small university, and you can see some of the images of my university in this video that is going around in this slide. So I'm also a researcher at the Telecommunication Institute, which is a national laboratory in my country, and we are divided in several groups: wireless technologies, optics and photonics, information data science, networks and services, and also basic sciences for supporting telecommunications. And my work is mainly on wireless technologies. So let me also briefly show what we do in our group. So my group is called Radio Systems. And in our group, we work on software-defined radio, 5G, 6G technologies, wireless power transmission, including RFID and Internet of Things, and also satellite new space communications and space and automotive radar technologies. So we normally work on the radio frequency front ends for all these activities and all these applications. But what brings me here today is mainly to talk and discuss how can we deliver energy and communications to several areas of the society, and with a special focus today on space exploration. And here I'm showing you one of the examples of what will be needed in the future for this type of space explorations. As you probably know, several countries in the world, including India, are trying to get to the moon and trying to get bases on the moon. And I took this photo actually from the European Space Agency. This is a very nice photo, a very artist impression of what could be a moon station. And what is interesting to see in this photo, that's why I bring it here, is that you see that the energy from this, for this base, actually comes from all these solar panels that you see around. And what is very interesting to see is that I don't see, at least visually, any place where they put their batteries to save energy. And why they need to save energy? Because in the moon, the energy is intermittent, and each 2 weeks you have sun, or each 2 weeks you have night. What that means, it means that if you base your solution only on solar panels, then, or you have huge batteries that can save that energy for you to use, or you have to get another source of energy in this situation. But in space exploration, there are other problems. And one of the other mission that I want to take here is also from the European Space Agency, is what you call the Rosetta mission. What was this? Well, this was actually a comet that was, a satellite, a probe that was sent to this comet, the Rosetta comet. And when actually this was going to this comet, what happened is that the satellite sent a probe to the comet. And when the satellite sent a probe to the comet, the probe should be put it in a place where you have sun all the time. So if you have sun all the time, you can charge your batteries and you can take your samples and send that information to the orbiter. Let me go back. You see, you have a orbiter here. You have, this is the probe. The probe was sent by the orbiter to the comet. And it's very interesting to see that our engineers were able to precisely put this probe into a comet that is moving. So this was amazing. But what you see is that when the probe got to the comet, the probe did not stop, and unfortunately went towards a shadow zone. You see, these are like mountains in the comet, and the probe was put it there. What was the problem here? Well, the problem was that the probe did not receive any more sunlight. And so after less than several days of taking samples, the probe died. So we spent a lot of money, we spent a lot of efforts to get this probe to a comet. And when it's on the comet, the probe died because it does not have energy. Another thing that I think it's very important to see in this example is that we only need 10 watts of power for this probe to operate. So you see, we should get other ways to actually power up this probe. And one of the things that I will show you today is how this orbiter, which is going around the comet, so this orbiter will have energy all the time, how this orbiter can actually power up this small probe. And I will show you how we will be able to do that. So what can we do for this type of space exploration and this type of problems with energy and communications? Well, of course, we can harvest clean energy. And most of the time, the clean energy that we would like to harvest is coming from the sun, but we can have other sources of clean energy. We can reduce the battery needs. And how we reduce the battery needs? Well, by using wireless power transmission combined with micro generation in local. And we can definitely, I will show you what we are doing to improve the energy efficiency electrical devices. And what I'm saying here is that despite this probe does not have any energy, probably I can continue to make a communication with the probe if we change the paradigm of the communication that we are using. And in that case, I will talk briefly about backscatter communications. So let me start first with the energy harvesting approaches. Well, you have light energy. Everybody knows you can transform sun to your electrical energy. You have kinetic energy, you have heat energy, and you have RF energy. So these are the four energy sources that are more available on the market. And here you can see how much power I can get from each one of these. And what happened is that energy harvesting, if you look to the light, as I told you, in the moon, we have a problem because 15 days we have energy, 15 days we don't have energy. Kinetic energy, you need to have something to create the kinesis. So you need to have something to move. It, of course, you need different temperatures to be able to do that. So one of the hypotheses that we are now looking at is RF energy. How can we get energy from RF signals? And how much power I need to operate this? This is another very important topic, because depending on where you're going to supply your energy, if it's a car, a mobile phone, an IoT device, a space station, or some kind of critical communications, the amount of power you need is really different. So you need to be able, before you start thinking, how can I remove the batteries out of my loop, out of my gadget, how much power I need. And as you can see here, above, I strongly believe that in the future, we should not have a single harvester, a single energy source, but we should combine different energy sources for our gadgets, for our devices. And these different energy sources will give you the amount of energy you need. And this graph actually comes from a report that is available online, where you can see that there are devices that work as low as 100 nanowatts, and there are devices that need, as you know, hundreds of watts or even kilowatts. And the other topic I want to bring here today is, if I want to communicate with my device, if I want to bring or get data from my devices, what can I do? And this is really interesting to see this graph, because this gives you the more or less the coverage distance that you have with different technologies available on Earth and the typical bit rates that you have. And what you see very interesting things. If you want low bit rate, low distance of coverage, well, you need low battery, you need low power, let me put it this way. But if you go to higher distances and high bit rate, then you need high power to operate these devices. But there are some solutions that start to appear for low bit rate, high distances, like LoRaWAN, Sigfox, that actually are standards that start to appear on the market that allow you to make a long range communication, at the same time allows you to not spend a lot of power. Of course, the amount of data that you are bringing from these devices is quite low. So there is a need also here in the communication framework to come up with different solutions, with different techniques to actually allow you to go higher than this distance, allow you to go higher than the bit rate with very low power consumption. And one of the things that we are looking in order to resolve this approach is really what we call wireless power transmission, or what I say here, wireless power transmission beam energy. What that means, it means that I will create a RF signal, electromagnetic wave. I will create a beam of energy, a beam of this signal, and then I will collect this energy on the other side, mainly using what I call an RF to DC converter. Well, the big problem with wireless power transmission at this moment, and has always been like this since Nikola Tesla presented this concept in the 19th century, it always been a problem because the efficiency that you can get from what I call DC to DC, because I want to generate a signal here, I want to receive a DC voltage here to power up my devices, and the efficiency is really quite low, because you need to go DC to RF, which is the oscillator, the efficiency is low. Then you have a power amplifier most of the time, low efficiency again, RF to RF, so the efficiency of your antenna. Then you have your beam, and then you have the RF to RF, again, our antenna, the RF to DC converter, and again, a DC to DC converter. And what is important to look here, the importance to look here is that all these efficiencies will not add up. They will multiply by each other. So one recent paper that was published in the Transactions of Microwave Theory and Techniques show you that for 1 kilometer distance, a WPT beam energy, the state of the art at this moment for 1 kilometer distance is around 2%. So the efficiency is quite low in this scenario. But that does not say that we should stop working on this. So I will give you some examples of things that are already being done over the world in this aspect. So the first one that I want to bring your attention to is the space solar power. What is this? Well, the concept here is very easy. You get a lot of solar panels in the out of space. These solar panels will conduct your sunlight energy towards a solar concentrator, and this solar concentrator will transform your solar energy back to DC, and this DC will then operate your RF signal, and you will have a beam of this RF signal to the ground. So this actually is not new. The first ones to present something like this came from the United States, from NASA. And then several other countries and several other nations have been pursuing this approach. Actually, I'm showing you here also a graph from the European Space Agency, where you have the same contact, you have solar panels, you have the RF beam energy, it beams to the ground and you receive. Well, if it is on Earth, of course, this will be a solution for the net zero that we are talking about recently due to the energy demands over the world. If it is for space, it can power up rovers, it can power up base stations, and so on and so on. So this is being considered really a solution for energy needs over the world. But it's not only this very, let me say, stringent and very important solution to bring energy to the ground. There are other solutions also being considered to use wireless power in everyday approaches in our day life. So this is one of the examples that is actually public. So Xiaomi last year present a long range wireless charger where they want to actually charge your phone while you are in your living room, and you can charge your phone continuously with a wireless power link. There are other companies, for instance, this is a company in New Zealand that is trying to actually bring energy to situations where you cannot have energy links by cable. So this can be done, for instance, in catastrophic situations, or it can be done in situations where to bring the energy, to put the power cables up to the for instance, as you can see below, to the power cellular base station, you can change the cables by a wireless link. And there are a lot of interest and a lot of advantages if you do that. Or there are also other solutions being thought which are not necessarily far field, what I call far field wireless power, but why not have your roads charging your cars, charging your metros, charging your buses? So what is the interesting if you do that? Well, the good thing if you do this is really that you don't need so heavy batteries in your car, in your bus. So your car can be lightweight, can be less expensive, and you can have energy continuously delivered to your car and to your bus and so on. And as I told you, there is also not only the NASA solution and the European Space Agency, but you have also an approach, and actually China is also looking to the possibility to get energy out of space and bring it to ground in a very, very important approach. And only for you to see, if you are interested on this topic, you can go to the Naval Research Lab in the United States website. And actually, they developed a very basic solution to show up how can you deliver energy over the air. And what you see here is astronaut Jessica Meir, where she is actually showing that a very simple device can gather and can harvest electromagnetic wave inside the ISS space station. So what you see is that really this is something that at first you can think this is like a science fiction movie, but this is not. This is reality, and there are a lot of solutions already in the market. And going back in history, when this really came up first was by Nikola Tesla. As I told you, in the 19th century, he predicted the first wireless power transfer experiment. As you probably are aware, so he predicted that we can send energy over the air. And then only 70 years later, another person called William Brown pioneered microwave power transmission, and he created what it's called a rectenna. What is a rectenna? Is an antenna that converts RF signal back to DC signal. And you can see here William Brown with something that is like an helicopter on his hand. And what you see here is really the experiment that he actually developed. So what he developed was a microwave generator that actually illuminate a reflector, an antenna reflector. This energy is sent over the air to an helicopter, and here you can see the real photo. You see here the size of the persons, the reflector is here, the energy is beamed to this helicopter, well, something like an helicopter, and he was able to put an helicopter flying without having any local energy, without having a local battery to power up this helicopter. So this was in the 60s, and then there was a lot of different experiments done by GPL and NASA, and actually this show for the first time that this is a viable solution with, of course, limitations, but this is a viable solution. Well, but as I told you, what is the big problem on this solution? Well, the big problem is that you have to convert DC to RF. You have to convert RF to RF. You have to beam this energy, and then you have to come again from RF to DC. And all these components have a different efficiency. So what that means, it means that in order to optimize this overall efficiency, I need to optimize the efficiency of the power amplifiers. I need to optimize the efficiency of the beam, so the antenna to antenna transmission, and I need to optimize the RF to DC efficiency, which most of the time is a diode based RF to DC converter. So I will show you now what we did in my university and what we did in this direction, how in each one of these elements, how we actually plan and how can we improve the efficiency in each one of these situations. So what we did was we combined wireless power transmission, we combined energy harvesters, we combined backscatter communications, and we build MMICs to actually gather all this structure. And this is what we called simultaneously wireless information and power transmission. And of course, what is our goal in my group? Well, the goal is mainly to have a significant number of sensors that you can spread around the moon or you can spread around the comet. And all these sensors will have transmit energy, so they will receive energy, they will be sensing your device, and they will communicate your data back to a low orbit satellite so that you can gather all this data. And again, the concept is quite simple for the wireless power transmission case. So you create your RF energy, you amplify that energy, you go towards an active antenna array so that you can create your beam of energy. On the other side, you have another antenna to collect these electromagnetic waves. You RF to DC, so you go through a diode, so you go to a rectifier, and you get your DC back. And as I told you before, the efficiency of all this situation is quite low because all these components are not 100% efficient. If they are not 100% efficient, it means that you have to multiply this efficiency by this efficiency by this efficiency by the RF to the RF efficiency and so on. So the overall point-to-point efficiency state of the art at this moment is around 2%. So we need really to increase this value. Here I give you a very simple example of depending on the frequency, what we can do, the amount of power we transmit, the distance. And as you can see, I think the most important of this graph is this DC to DC efficiency. You see 2%, 2.3, 1.5, 1.25. So this is really low. We need actually to redesign the system so that we can operate with higher efficiencies. If not, this is very, very a situation that is very complex to actually prove that it can be a solution for other approaches. And I told you, we have to look carefully to the power amplifiers. We need to look carefully to the beam energy, the transmitter antenna gain, the receiver antenna gain, and the overall beam efficiency, and the RF to DC converter. And in this slide is very interesting to show. And you see here, for those that are RF engineers that know communication over free radio communications, you know that normally we use the freeze formula. And when you are a telecommunication engineer, a radio telecommunication engineer, you normally use the freeze formula, and there is a coefficient called lambda over 4pr squared. This coefficient is what we call path loss, which means that we assume in telecommunications that we are going to have a loss in the communication between the receiving and transmitting antenna. But this is something that we need to change in this concept of wireless power transmission. We cannot have this loss. So we need to change completely. How can we look to this loss? So let me go point to point to see what can we do and what we did in my group. So the first thing we did was to actually optimize the efficiency of my power amplifier, of my transmitter. And in order to do that, we have been working with gallium nitride transistors in actually to increase the maximum we can in our transmission situation. And it's very important here because I want to send a signal over the air, and I don't want to have harmonics that actually can dissipate energy over the other frequencies. This is one very important topic. So the transmitter we actually build is an active antenna array. You can see it here. We have 16 elements in our antenna array, and we can play with the power, amplitude, and phase of each one of the elements to beam energy to each one of our sensors. And by doing that, we actually use a feedback channel. So what we do, we send energy to the sensor monitors how much energy is receiving and informs the transmitter how much energy he is receiving. Why is this important? Because with this feedback channel, communication channel of how much energy I'm receiving, you can optimize your antenna array to maximize the power in each one of these sensors. So here you can see actually our prototype. It's a simple 16 elements. These are the receiving antennas for the feedback channel, which are backscatter. I will tell you a little bit more on this. And this is the back side of this. So you see that each one of these elements have a power amplifier that is here, and inside these boxes, you have your phase shifter and so on. So we can change the amplitude and phase of each one of these elements to create a beam of energy. Well, but this was not enough. Why? Because if we do that, we are assuming a traditional telecommunication design, which means that you are optimizing the antenna gain. And I'm not interested on the antenna gain. I really want to transmit energy. So what we thought was, can we actually, instead of creating a beam of energy, can we actually create a focus of energy? Can we focus the energy on a certain point? So we come up with an idea, a very simple idea, first experiment. I don't know if you ever gone to a children museum, science museum. You normally, when you go with children to these science museums, you see that one of the experiments that all museums all over the world have is two parabolic where you can talk in the focus. And normally you put your kid on the other side of the room on the focus of that parabolic also. And when you talk on the focus, your kid will hear perfectly what you're saying, despite he's on the other side of the room. So we bring to this concept the same approach. What you see here is really one of our antennas. So this is a horn antenna. It's connected here to our network analyzer. And here you have a parabolic and another parabolic reflectors. And this focus and this focus are exactly at the same distance. So by doing this, what we collect was we submit energy to this reflector sent to that reflector, and you receive energy there. So we show that we get 65% efficiency at a 6-meter distance. What is the problem here? This receiving antenna should be on the focus. If you move slightly from the focus, you lose all your energy. So this is really a big problem. Well, the other problem, after you go through the air interface, the other problem is the RF to DC converter. In the RF to DC converter, we use diodes. So it can be a single diode, it can be a Dixon multiplier, something like this. And what normally you do, this goes a lot to electronics, but what you do is mainly that you don't bias your diode, sorry, because this is wireless power transmission. So your diode start at 0 volts, and then you put a sine wave, an electromagnetic wave, and what you see is that it goes through this knee, and when it goes through this exponential curve of your diode, you start to rectify your diode. So you have a DC voltage here that is proportional to the amplitude of this signal. And what is the problem? The problem is that, well, there are two problems. The first one is you have a self-bias of your diode. So this, as you go through this need, this goes slightly back. And the other problem is this breakdown. So if you increase a lot your power, you get breakdown very fast. So in Aveiro, we come up with another idea. Why we are sending a sine wave to the air? I can play with my waveform. I can send other waveforms to the air. So we assume that we can send other waveforms that excite more this exponential curve of this diode. And so we actually, as you can see here, in this situation, we use a multisign. What is a multisign? Is an addition of different signs. So by adding different signs, what we were able to do, we were able to excite much more your diode, so your DC voltage goes up. And so this was one of the things that we did, and we actually get quite good results. As you can see in this graph, the DC voltage for one tone is the blue one. As you increase the number of tones, you go up. So you get more DC out of that, so you get more efficiency. What you see also is that if you get a lot of tones, if you have a lot of signs, then it comes down again. And why is this happening? Because if you see this peak goes in this direction, but this peak also increases. And when this peak starts to touch the breakdown, you can increase the peaks, but it does not make any sense because it goes to the breakdown. So by doing this, we were able to actually increase our efficiency, increase the overall efficiency of our system. So the other problem I have, as I told you, we are sending power over the air to power up my sensor, but we also want to send information. And how can I send information over the air without energy needs, reducing the energy needs I want? So I will give you an example. I hope you can hear the sound that I will show you now, because the concept that I will talk to you about is,
when I come from
let me go a little bit before I start that video. What I will show you is an idea from a inventor called Theremin. And actually, he produced music instruments. And it's very interesting because by producing a music instrument, we are going to see that he revolutionized the wireless information communications with that. So I will play this small video and then I will explain what is there.
And there's a little trick. When I come from finger position 8, I will first only move my fingers. And then if I go to this position, which I call position 5, then I will also move my wrist and turn it and close my fingers together.
Okay, so this was a very short movie. What I'm showing is a theremin. Actually, this is low-end theremin with this first equipment. So this is a musical instrument. You see, you have an antenna, you have another antenna, and what this lady is doing, this creates a resonant electromagnetic field here. And if you put your hands in the middle of your field, you change the audio. So how is using this? Well, what is doing is mainly to use the backscatter signal. So by receiving a backscattered signal with your hands become your antennas. By doing that, he was able to actually create a music instrument. Well, but this person was able in 1946 to actually create the same concept and bring it to the first zero power batteryless microphone. What he did, and actually this was a spy equipment, he actually put inside a complete wooden box, he put a thin metal ear. And what happens is that this thin metal is nothing more than a dipole antenna. And when you talk, you have a resonance. This whole ear is actually a resonance to your voice. and you have a tiny piece of metal there also. So when you talk, what happens is this tiny piece of metal change the impedance of this antenna. And by doing this, it creates the first backscatter radio, which is the basis of all RFID, radio frequency identification tags, that you have all over the world. So if you look, actually, this is Americans complaining about this spy equipment. And if you look here, what you have your antenna, you have a signal that goes to your receiver. And if this receiver, this antenna is short circuit, a signal comes back scattered. If the signal is matched to a 50 ohm, no backscatter comes out. So by doing this, we are actually able to put information on top of my radio signal and transmit information without the need of any power, you see, because you are only changing the impedance of your receiving antenna. So you have your wave generator, it goes to your signal, goes to an RF to DC converter, converts this back to energy, power up a microcontroller that is going to be connected to the backscatter. And the backscatter, as you see here, is nothing more than a switch. So it's a transistor, a single transistor. So if you switch it on, you create a short circuit. If you switch it off, the antenna will be connected to RF to DC converter and will be matched. By doing this, you can actually power up your device by using wireless power transmission, and you can transmit your signal back without any need for energy. So very, very low amounts of energy you can do it here. So I will show you very fast what we did in Aveiro. So our first circuit was like this. So we have a circuit for the RF2C converter, connects to a microcontroller that goes to this backscatter modulator, which I told you is mainly a switch. Then, but unfortunately, this only allows you kilobit per second, which is more or less what RFID allows you to do that. So we do amplitude shift keying communication. Then we increase the data rate. And how we increase the data rate? Well, we create the first IQ backscatter modulator. So it's like, if you are familiar with quadrature phase shift keying or quadrature amplitude modulation, we did quadrature amplitude modulation on top of backscatter. So here you can see our IQ modulator with 2 transistors, and we were able to go to gigabit per second with our first experiment. Then we add to this gigabit per second modulator, we add our RF to DC converter to get energy out of this. And with that work, as you can see here, this is normally what is other techniques go. So this is the bit rate, this is the power consumption. We were here, so we were very low power, but at the same time, we could achieve very high bit rate for this situation. And then we, of course, this was a large prototype in the lab. We actually built a MMIC circuit. You can see it here. And this there, and we connected to a very small antenna just to show that we can actually bring this wireless power to a very, very tiny equipment. This was done for 28 gigahertz. And what is our goal? Well, our goal is to have our passive sensors, to have wireless power transmitters all over the place, and to have low cost software-defined radio that can receive that information and receive and actually demodulate that information from our passive network situation. So I think this concludes my talk. I think I'm on time, and I want to thank you very much again for inviting me to be here. Let me say that if you are interested in wireless power, there is a website from IEEE, which is wpt.ieee.org, and feel free to go there and see actually what are the activities around the world on this technology. Thank you very much.
Thank you, sir, for sharing your valuable thoughts with us. Your words were full of enthusiasm and valuable knowledge. Students, any questions? request you to accept this e-memento as a token of gratitude. Please, sir.
Thank you. Thank you very much. Thank you. It's a pleasure to receive that. Thank you.
Thank you, sir. Thank you very much. Hello, sir. Thank you very
Yes,
much.
yes.
Thank you.
Thank you very much.
for presentation. Actually, I am also doing research in this field only, sir.
Okay, good.
I'll contact you later.
Yeah, feel free to send me an email. It's a pleasure.
Thank you very much.
Okay, thank you.
At what time now at your place, sir? Where Portugal? What's the time now?
The time now it's 10:13 a.m.
Morning.
morning. Yeah.
Super, sir. Actually, I was a little bit confused in choosing the time slot because we invited speakers from different parts of the world. So,
Yes. No problem. No problem.
yes. Thank you, sir. Thank you very much.
Okay. Thank you very much. Goodbye. Thank you.